Hi everyone, I'm Jian Zhang. Today I'm going to talk about how to create oriented filter in the Fourier domain. During our class, I remember that professor showed a really cool idea that if we compute some image FFT and then zero out high frequency in one direction, we can simulate a motion blur. Today, I want to take that idea further. Instead of zeroing out a direction, what if we keep only one direction and throw away everything else? That is oriented filter does. Let's get into it. Um, just a quick context on where we are. We already covered the 2D Fourier transform. We know that the frequency domain looks like how the center is low frequency and the edge are high frequency. We have already seen the low pass and high pass filters. When we zeroing out the outside, it blurs the image. And if we zero out the center, it gives you a very dark image because we only have the information of edges, so we don't have the average brightness. Today, I want to add a new dimension. Instead of filtering by frequency, we filter by direction. And this leads naturally into Gabor filters, which you will see later in this course. Let me remind you of something emphasized last class. When you look at the FFT of an image, every pixel tells you two things. Its distance from the center tells you the frequency, how fast the scenes are changing, how fast, like the sine wave, how long is the wavelength. And the angle in that frequency domain relative to the center tells you the orientation, in which direction that change happening. So if you see a bright dot up here to the right of the center, that means your image has a strong sine wave component that is fairly high frequency and oriented in that direction. Here is a key Here is a key point. Mhm. Direction is already explicitly encoded in the frequency domain. The position of each pixel is basically it's a name tag. It says I'm this fast. I'm pointing this way. So if we want to filter bad direction, we just need to pick which position to keep. And let's start with the simplest principle-oriented filter, which is actually what Professor showed in last class. Remember when he talked about zeroing out a horizontal bar in the frequency domain, the horizontal bar in the FFT contains the frequency component responsible for vertical structures in the spatial domain. That is because the perpendicular relationship vertical edges have the intensity change in the horizontal direction. So they show up as a horizontal frequency. Um, so here's the idea. If I keep only the horizontal bar and zero out everything else, what happens? That is a up level picture shows here. I can keep the horizontal bar zeroing everything else. We can also do the opposite operation, which is we keep the vertical bar, and the result is we're blurring out the horizontal. Um, we're blurring out in the horizontal ways. So that is already a working oriented filter. It's just a line through the frequency domain, and it selects one direction. The first example, the direction we select in the frequency domain is horizontal, and the result we get is we only keep the perpendicular information, perpendicular frequency informations. And in the second example, we keep in the frequency domain, we selected a bar in the perpendicular direction, and the result is we only keep the information uh, horizontally. And the next step is the solution is the next step is what if I want to select a filter at arbitrary direction, like 45 degrees or 37 degrees. The solution is to think in polar coordinate instead of describe each frequency point as x and y in Cartesian. We should describe it as r as a distance from the center and the theta as an angle. The conversation, the 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 converse is straightforward. R equals the square root of u and v, and the theta, the theta is the arctank of v and u. So this is the idea of how we select a filter in arbitrary angle. Okay. And so here is a full process, step by step. Um, Step one, take your image, compute the 2D FFT, shift it to zero frequency. Is at the center here. Um, Step two, build your wedge mask. Pick your target angle theta zero, and your bandwidth. The bandwidth is how much angle difference you want. Um, so we have to do two symmetric wedges. The step three, multiply the FFT by the mask, element by element. This is actually the filtering. Every frequency component outside the wedges get zeroed out. Step four is inverse FFT to get back to the spatial domain. And just like Professor Maxwell showed with the Gaussian filter in the frequency domain, it doesn't matter how big or complex your mask is. The computation is always the same. One FFT, one element-wise multiply one inverse FFT. Let me show you this in action. Here's a building image uh, at the left bottom here. Um, it has vertical window frames, horizontal floor lines, and some diagonal shadows. When applying a wedge at 0 degree with delta theta of 15 degree, the result keeps only the vertical structure. Notice how clean the separation is. The floor lines are completely gone. Rotating the wedge to 45 degree picks up the diagonal feature, and at 90 degree, only horizontal structure survives. Each result is like peeling off one direction layer of the image, and if you add all the layers back together, you'd approximately reconstruct the original, because together they cover most of the frequency energy. One more thing to understand how the bandwidth theta change your result. With a very narrow bandwidth, like 5 degrees, the filter is extremely picky, almost like a line. Only structures very precisely align with your target angle get through. The result is sparse. At 15 degrees, you get a good balance, selective enough to isolate the direction, but also wide enough to catch real-world features that aren't perfectly aligned. At 30 degrees, the filter is more permissive, and the result starts showing more of the original image. In practice, 10 to 20 degree works well for most applications. The right choice depends on how selective you need to be. To wrap up, an oriented filter in the frequency domain works by keeping frequency component in a specific angular range and zeroing out the rest. Three key takeaways. First, the simplest version is just a line or bar in the FFT, like Professor Maxwell showed in his class. To generalize to any angle, switch to polar coordinate and use a wedge mask. Second, always include two symmetric wedge because of conjugate symmetry. Third, the bandwidth delta theta controls selectivity. Narrow for precision, wide for more inclusive filtering. Looking ahead, Gabor filter reaches the same directional selective, but in the spatial domain. In the frequency domain, a Gabor filter um, looks like a smooth elliptical blob, essentially a softer version of the wedge mask we built today. Thanks for watching.